Hello, welcome to another video about Smar technology. Let's now discuss the educational aspect of the didactic plant PD3. Let's talk about the characteristics and how this plant operates. With the didactic plant, we can create accurate simulations of an industrial setting in a learning environment. This allows us to create closed loops. Through the resources of our didactic plant, we can do various simulations and control strategies. This includes simple strategies as well as more complex ones. With actual engineering tools of engineering, we can configure the whole system of the didactic plant using System 302's tools. There is also a supervisory software integrated into the plant for the operation and monitoring of the control loops of the didactic plant. It is real software used industrially, and you can operate the whole system with it and visualize the entire functioning of the didactic plant. This didactic plant comes pre-configured with some control strategies and screens from the supervisory and monitoring system, but you can additionally configure your strategies and screens of your supervisory system. In this didactic plant, we can work with various technologies. We can work with controllers, with Foundation Field Bus. We can work with the existing HART technology. We can work with Profibus technology. And to communicate with the supervisory system, we can utilize OPC for this purpose through the Ethernet network. Now let's analyze the operation of this plant. We have a tank here which serves as a reservoir. This reservoir is designed to hold water. It will feature an external water supply for both inflow and outflow to the network and sewage system. We have two pumps, one on the left and one on the right. Connecting the pump, we direct water into the left side circuit, going through a flow meter with an integral orifice, and then through the valve. This valve has a bypass if manual mode is needed, and goes to a heating tank. This heating tank has two heating elements, which will serve to heat the tank. Additionally, there is a temperature gauge, and we have a level meter besides the flow meter we mentioned here. So we can work here with the temperature variable. If we prefer not to use temperature, no, we can work with level, and we can handle flow too, the primary variables. On the other side, it repeats the same control network or a similar one. By turning on the pump, it sends water to the circuit, goes through the flow meter, passes through the valve with a bypass, and comes to a mixing tank. We refer to it as a mixing tank since we can introduce hot water from the heating tank when managing temperature, and introduce cold water. And then we blend hot and cold water to achieve some more advanced control strategies. We also have a temperature gauge in this tank. We have valves to release return water to the reservoir, and we also have consumption valves There are 4 valves here that will simulate the consumption of the mixing tank. Essentially, this is how the educational plant functions, its circuits. Later on, we will explain in more detail its components. We will divide the educational plant into 2 control networks, as we have 2 valves allowing for 2 independent systems. Or we can implement advanced control strategies using both valves and the control networks together. Then on the left side, we have a control mesh that I called here a mesh of one, where, as we have already explained, connecting the pump, it goes through the flow meter, allowing us to establish a control of flow via the proportional valve that goes to this tank, and this tank serves as an upper water reservoir. This reservoir here, when it is full, it has a water outlet at the top that goes to the mixing tank. So the heating tank, as it fills up, if I do not open the valve that returns to the reservoir, it flows and the water is directed into the mixing tank, which may return to the main tank. Thus, we refer to this control grid as a mesh of one. Here we have a real image, a real photo of the mesh of a mesh of one. So again, when the pump is turned on, the water enters the circuit going through a rotometer for flow measurement indication, goes through the electronic flow meter with an integral orifice, goes through the valve, equipped with a positioner, and enters the heating tank, returning either to the main tank or back to the mixing tank. On the right side of the plant, we have what we call the mesh of one, which we refer to as the mesh of one. Within the mesh of one, let me clarify again, the pump will go through a rotometer. It passes the flow meter. It goes through the valve with bypass and comes to the mixing tank. The water can flow back to the main tank via the consumer valves or through another direct circuit without the consumer valve. Once more, we have an actual photo of the mesh of one. The main tank, the pump will pull. It will pass through this rotometer here on the right via the flow meter. It passes through the valve with a positioner and comes back here or goes to the mixing tank. We have here the consumers where the water can return and close the circuit to the main tank. Let's now discuss each component of the educational plant in detail and their roles. First, let's talk about the water reservoir, which is the main reservoir of the didactic plant. Here we have the image of the main reservoir. This main reservoir is fed through an external water source, and we have a float inserted in the main tank. This float will mechanically control the level to avoid overflow, and thus we can do it automatically. Fill the bottom tank. In this image, we observe the external feed to the primary tank. Here are the water outlets that will direct water to the sewer. Let's discuss the 2 pumps present in the educational setup. We have 1 pump on the left side and 1 pump on the right side. They all have valves to block or release the flow of water in a system. which will direct water into the main circuit of the plant, sending it to the measuring equipment and directing water to the upper tanks. Let's discuss the valves and the bypass now. Inserted in the teaching plant, we have the valves on the left side of 1 and on the right side of 32. The valves are control valves that work with pneumatic control. We have a positioner for signal conversion. For the electrical signal sent to it, the control signal, for the valve to function. This positioner, the FY, will take the information from the main controller and make the conversion to air, allowing us to transform the electrical signal via a pneumatic signal for valve control, including its opening and closing. It is a linear valve, and we will receive feedback from this valve using a magnet and a Hall sensor. The magnet will be fixed to the valve. It will operate the valve, so the Hall sensor, an electronic sensor, will determine the precise position of the valve as indicated by the main controller and maintain the water flow at the desired position. We show here again the valve with the positioner, which is, after all, a very important element in control loops in industrial automation. Here we have the valve. This valve is a linear valve. As the valve stem operates, a magnet will be present, which will move and create a magnetic field, which via a Hall electronic sensor will detect the physical mechanical position of the valve. The HL sensor will send the information here to the positioner's electronics, and it will confirm if this information corresponds with the control data it receives. We also possess, besides the automatic controller, we also have a bypass where we can manually operate the plant, allowing us to close this valve and that valve. We eliminated the main proportional valve, and thus, through the bypass, we managed to introduce water into the circuit for our flow meter and our tank. Let's discuss the flow meters present in our Darty facility. So here we have a rotameter. Water goes through the rotameter, a flow gauge, and then it goes to the electronic flow measurement equipment with a built-in orifice. This will transmit the information to our controller to allow us to electronically obtain the flow signal. Let's discuss this heating tank now. Here we visualize the heating tank. It has two heating elements that will warm up our tank. We also have a level device that will check the level. The resistor is only activated for heating when this level exceeds the height of the resistors. So it keeps monitoring the height to avoid burning the resistors. We also have a temperature switch located on the tank. This switch will check the tank temperature, preventing it from exceeding 90 degrees to avoid water evaporation and turning into steam, and exceeding 100 degrees. In this tank, we also have a temperature transmitter that measures heat. It will carry out electronic measurements. To the left, we see that the mesh is 31, which pertains to the heating tank. There is a PT100 located there. To the right, we will find a thermocouple positioned. Now we will discuss the mixing tank. Within the mixing tank, there is a cold water circuit that originates from the main tank. And we can also have hot water coming from the heating tank. There is also a level gauge here, similar to the one in the heating tank, for level monitoring physically. Here, we also have the consumers, where we can open or close the valves to manually determine the tank level. Additionally, we have a temperature transmitter that will electronically measure the temperature, enabling us to relay this information to our main controller. Here we show in detail the consumer valves we have that we can open manually, and the return flow of this water, whether heated or mixed, returns to the main tank. In this photo, we see a model of a controller with a panel set up in the facility. A possibility exists to utilize foundation field bus technology, Profibus or HART, as we have explained before, and using the internet or a PC to operate supervisory systems. This panel was developed in various versions depending on the school and its needs. To supply the valves, we have a filter here, where we connect the air intake, allowing us to control and filter the air supply to the plant for teaching. The educational plant typically has a frequency inverter to manage the pump speed. So we have this possibility. And we have a PWM converter too. This PWM converter receives the signal from the controller and pulses the resistors as programmed by the controller to 0, full control. In this figure, we display the main panel of the educational plant. Here is a button to turn it on, the teaching plant. An indicator shows the panel is powered. There is also an emergency button, indicating an emergency. We can also operate it manually and automatically via the supervisory system. The pump has a switch to turn it on and off, and we also have a button to turn pump 2 on and off. Each pump is equipped with a signal indicator in the center that shows if it is operational or not. Additionally, there is a lamp that provides us with information if the plant's temperature is high, and we also have a signal indicator here if the level is low, preventing the resistances from turning on. It features a siren to set up an alarm system, plus a button to turn off the siren to prevent noise. There are various panel versions for the educational model. Based on the requirements of the educational unit, we created the main panel. Here's another panel version, featuring the buttons we discussed before. This shows the plant rotated with the controller and the panel oriented towards the front of the educational model. Regarding the software used, we utilize System 302. And within this software, we centralize all the applications we can use in the didactic plant for configuration and monitoring of the system, of the teaching system. The software has a hard key for the supervisory system, and a hard key for the System 302. When using the plant with the LC800, you need the LC700 license. System 302 is a big deal. This plant is equipped with wheels to make its movement easier. at your school unit. We can work with the didactic plan using the pillars of Industry 4.0, work with simulation, focus on safety, cloud technology, big data, and augmented reality, and we can also work with the Internet of Things. We present an example of our monitoring system, which monitors the educational plant. And also through a mobile phone, we are showing augmented reality here. It is entirely possible to integrate with Industry 4.0 and the digitalization of the educational plant. With this explanation, we finish the basic overview of our educational plant. And for any inquiries, you can contact us at the following numbers: